Today we're going to be talking all about how gravity affects acceleration. Let's say you have a juggler and they're juggling obviously more than one ball at a time, but this guy here is just starting out, so he's learning. And he's throwing the ball up and it's going up and it's coming down. We're talking about acceleration. The phenomenon that we're going to base this around is juggling. So acceleration is a change in velocity over a change in time. Now, that could mean it's speeding up, it could be slowing down, it could also be changing direction because acceleration is a vector. And we learned our basic formula was delta V over delta T, or V2 minus V1 over T2 minus T1. Now, so far, all we've really studied is acceleration and velocity in the horizontal direction. We didn't really look at the up and down. So we're going to get into the up and down today. So keep our acceleration formula in the back of your mind when we think about the y direction, the vertical up and down. We can credit Galileo for figuring out how acceleration is affected by incline. So if you had a ramp and he was studying rolling balls down ramps, the steeper the ramp that we got, the more closer it got to literal free fall. So if you just ignore any wind and air resistance when the ball is rolling down or falling, the velocity increases more and more as more time goes by. So this is an indicator of acceleration. So it's an acceleration in the y direction. It's an acceleration that does not change. We say this acceleration is constant, okay? Now, a skydiver is under the influence of gravity, but they're also under the influence of air resistance. So free fall is a very special occasion where the only acceleration acting on it is gravity, and there's no other force like air resistance acting on a falling object. This is always going to occur at negative 10 meters per second squared because it's downward, or more precisely negative 9.8 meters per second squared. We can get from this constant acceleration several values. We're going to say that the acceleration due to gravity can be represented by the letter little g. And under this situation, it has to be dropped. You can't just throw something down, okay? Now, formula for finding how fast things are going are based on how long they've been under the influence of little g. So that's going to be, our velocity is going to be equal to little g times time. So here's a couple of examples. After 1 second, you're going 10 meters per second. And after 2 seconds, you're going 20 meters per second. And after 30 seconds, after 3 seconds, you're going 30 meters per second. So if I multiply my time 3 by my little g 10, I get 30 meters per second. That's a downward velocity, and it's a downward acceleration. But it does get faster and faster the more we fall. Since little g is constantly 10 meters per second squared, the more time, the more velocity. The other thing we can find from free fall is the distance that an object falls. So little g is constant. That allows us another trick of our trade here with the equations. I can say that the distance is half of little g times the time, or half of little g times the time squared. And if you want to shorten that, you could take half of 10 and turn that into 5 and make that 5 times your time squared. So a couple of examples under free fall acceleration. It's always going to be 10 meters per second squared, half of 10 meters per second squared, times, let's say, after 1 second. Well, half of 10 is 5, and 1 squared is 1, so our change in distance should be 5. This is a change in distance in the y. It's also going to have to said that's changed down, or that it's called a negative 5 to indicate that direction, okay? Now you've just learned 2 equations that work in free fall. Again, free fall is a special situation. Our acceleration is constant. It's due to gravity. I can never turn it on or off. It's just always there. So it's always a negative 10 meters per second squared for little g. We can find velocity if we multiply little g times time. And we can find the distance if we multiply 1/2 little g times the time squared. So a trick to get the time then is rearrange this equation. Time is going to be equal to the square root of 2 times the distance divided by little g. Let's take a look at the data from our juggler. It turns out that even though the position of the ball can go up and then down, its acceleration and velocity are always in the negative direction, always going down. So gravity always going to be pointing down at 10 meters per second squared. Now, does this always apply to other situations? Let's look at dripping water. All of our objects are going to fall with a faster rate the more time goes, and all of our objects are going to fall farther. But are all objects going to fall at the same rate depending on their masses? Let's see. My tennis ball is weighing in at a whopping 56 grams roughly. And I'm going to compare that with a rock, a little bit heavier, about 109 grams on our scale. So they have different masses. The rock has more mass. Which one's going to fall first? Our rock, with about double the mass of the tennis ball, lands at the same time. Wowzers. Now, looking at the data, we get their expected position versus time graph on the top with a curve that indicates our acceleration due to gravity, little g, and the velocity time graph shows an increasing velocity. These are just going in the negative direction. Okay, since everything is going downward, our data is going to be pointing to the negative. Now, what happens when I take a rock and a piece of paper? Womp womp. Oh no. Unfortunately, the paper requires too much air resistance to be a good candidate for free fall. It'd be like dropping a feather or dropping a hammer. The hammer is going to sink immediately because of less air resistance, but the feather is going to zigzag while the hammer goes splat. They did this on the moon with no air. There's no atmosphere.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
So if we can neglect air resistance, then we can have objects falling at different masses at the same rate. Let's try this from the roof of Trinity. Here's 2 water balloons of different masses. Hold your breath. Boom. Physics works. So it just turns out that air resistance is the enemy of free fall. Air resistance is going to slow you down. It's going to change your velocity. That's great if you're a skydiver using a parachute, but it's not great if you're a physics student in class. So we want our velocity to not be changed by air resistance. A good example for free fall is something like a ball. Okay, we can always easily ignore air resistance in our ideal problems that we do. And remember that acceleration due to gravity, or little g, is always going to be a downward 10 meters per second squared. Even the accelerometer on my phone tells me that little g is about 10 meters per second squared. Here's a word problem that you can apply to your take-home quiz. Let's say the teacher accidentally dropped a water balloon on a freshman student, and it took a total of 3 seconds to hit that student. Let's find out how high they were when they dropped the water balloon. We're given the time 3 seconds. We know that little g is negative 10 meters per second squared. We can use our equation that the distance in the y is 1/2 g times time squared, and plug and chug. What we end up getting is a negative 45 meters because it was 45 meters downward. So how high were they? They were 45 meters in the air because it was a negative 45 meters traveled. Now, what happens if we're given a distance? Say we know that there's a tower and it's 45 meters high, and you dropped a coin from the tower. Could you find out how long it would take for the coin to reach the bottom? Well, 45 meters is my height. That's given. I know that little g is going to be negative 10 meters per second squared. What kind of formula could I be using? Let's take a look at some of the formulas we looked at earlier in the video and see if they work. No, that one is not going to work. I need to solve for, do I need to solve for little g? No, I know what little g is. That one's not going to work. What's another formula that we learned? I learned velocity is little g times time, but I don't need to know velocity. I want to find how long it's going to take. So I want to find time. It's going to be the square root of 2 times the distance in the y divided by little g. So I have distance, and I know little g is negative 10. So 2 times my negative 45, because I'm going downward 45, is going to be negative 90 over negative 10 inside that square root symbol. So that's going to be negative 90 divided by 10 is going to be square root of 9 positive. And the answer is going to be 3 seconds. It takes 3 seconds to get down there. Okay, summing up, little g is always pointing down. It's a vector. It's always working. It's always negative 10 meters per second squared. Oh, yeah. And we, of course, have these same equations in our packet from earlier. And we're checking the boxes on velocity. We're checking the boxes on distance. We're checking the boxes on time. There it is, folks. Enjoy it, and bye.